Hello, hello, hello. Hello, everybody. Apologies as usual for the very untimely restart at the start of every stream, but what can I say? I should really figure out why the audio goes funny if I don't do that, but also, as I'm sure you all gathered, I'm quite lazy about this kind of thing, so it'll do. If it works, it's fine. Yeah, so hello, Slayer Darth, thank you for saying hello, that's very nice of you. And yeah, tensors today, Atom Fighter, exactly. So this is quite a. I've sort of written. I was thinking about how to answer this, um, in a sort of non-fake way, because of course the general thing people say about tensors, the meme of what is a tensor is, well, a tensor is something that transforms as a tensor, which is a bit of a sort of ontology, really. It's not not a very satisfying answer. So I'm going to try and give an idea of what a tensor is from a slightly more formal background. I will skim over some things, and it will also, I guess, be kind of rushed. So if you've got no idea what a tensor is, no idea what a vector is, this may be just a little not too helpful. I'm going to use my Mickey Mouse hands. I do love my physicist Mickey Mouse hands. I'm not a mathematician, so I won't pretend I am. But yeah, hopefully we can get an idea anyway of what I understand a tensor to be, of how I think about tensors. So, the first perspective I want to think about is a perspective from linear algebra. Okay, your tensor knowledge is meh. Well, that should be fine. I mean, meh is probably good enough. If you got a little bit, as long as it's not non-existent, then that should be fine. We should be all right. So, as usual, though, any questions that come in as we go, please do feel free to put them in, and we can think about those too as we go along. But this is the general kind of presentation I've been thinking about giving. So the question is, what is a tensor? And I'm going to try and refrain from saying something that transforms as a tensor throughout, except in a jokey way, of course. So the first perspective I want to think about is the perspective from linear algebra. But before we think about what a tensor is, I think it's actually important to think about what a vector is in terms of linear algebra. So we have this sort of understanding of what a vector is as being, in a very elementary way, something that has direction and has magnitude, which distinguishes it from a scalar, which we just think of as a number, a real number, or a complex number, which is just a single element, a single thing. Vectors we sort of think of as being built from multiple scalars. So this immediately is this idea of having, column vectors or row vectors, where your vectors have components. But of course, to think about components, you have to be thinking about a basis. You can't have a component without a basis. It doesn't make sense to talk about vector components without specifying the basis of which these things are components in. So before we talk about components and bases, let's give the sort of slightly more formal definition of what a vector is. So formally, I will describe a vector as being an element of a particular algebraic structure known as a vector space. And this argument still seems a little ontological, saying, well, a vector is something that's in a vector space. Well, what is a vector space? Well, the motivation for doing this is that, we have an idea of what a vector is in terms of our very basic idea of it's something that has a direction and has a magnitude. But of course, that is not a particularly formal statement as far as a mathematician would be confirmed. Hello, non-dairy. Non-dairy neutrino. I don't know if you prefer non-dairy or non-dairy or neutrino or dairy neutrino, but I guess I'll just say non-dairy neutrino in full. So of course mathematicians would not be too happy with this very generic statement of what a vector is, something with direction and magnitude. So gluten-free neutrino. So they want to generalize this concept of what a vector is. And the way this is done is through this idea of a vector space. So the way we could approach this now is to just state all of the axioms that describe a vector space. But actually, I think that would be a little bit boring, so I'm not going to do that. But what I'm just going to say is that a vector space is this kind of generalization that a mathematician would make to describe the properties that we all think are fairly obvious that ordinary vectors have, thinking about them as arrows and directions. Okay, so a vector space is this formal algebraic structure which generalizes these sensible properties of vectors. And I'll explain what I mean by sensible properties in a minute. So the notation I'm going to use, all the way throughout, I'm going to be thinking about column vectors and row vectors, about ordinary real vectors. I think you can get needlessly abstract with this stuff because a vector space is an abstract structure. You know, it can be used to talk about things that seem totally different from column vectors, row vectors, and the image of an arrow with a direction. But in our conversation, we're just going to think of a vector space as something which describes these directed arrows that we sort of understand vectors to be. We don't need to get needlessly abstract with it. Okay, so when I think of a vector space, I'm going to think of the vector space as being the collection of all of these different n-dimensional column vectors. So an n-dimensional vector space over the real numbers, I will just think of, hello Sly, hello Sohail UAE 2013. It's a bit of a harder one to say. So I will picture a vector space as just being a collection of these n-dimensional column vectors. Okay, so this notation here I've drawn, I've just realized this is inconsistent. Later on I tried to color code things, but I realize now that I switched my color at some point. So this should be orange. So this notation here is for an n-dimensional vector space over the real numbers. That just means, again, thinking in this simplistic way about vectors, that all of our components are real numbers. They're not complex, they're not imaginary, etc. So without stating axioms, like I said, I didn't want to describe a vector space purely by a list of axioms because, frankly, I think that's a little bit boring. A vector space is just something that generalizes the concept of a vector, and by generalizing it keeps these important properties like linearity, closure, and instructions on how to multiply the vector by scalars. So by closure I mean if I take any two vectors in a vector space and I add them together, the resulting object is still in the vector space. So, you know, if you take a three-dimensional column vector and you add it to another three-dimensional column vector, the thing that comes out the other end is still a three-dimensional column vector. Again, this seems like an obvious statement, but it's important mathematically to describe this. Linearity as well, as in these things will all, you know, add linearly. If you multiply one of these vectors by a scalar, it will still be a vector in the vector space, and so on. All of these different properties that we kind of understand intuitively vectors to have. But you'll know that we also have a different way of writing vectors. We don't necessarily have to write vectors as column vectors. We can also write them as row vectors. So I'm going to write a generic row vector in this way with a transpose sign. You know, a transpose sign just means you kind of swap the columns of the vector with the rows of you swap the columns of the matrix with the rows of the matrix. So if you take the transpose of a column vector, it just turns it into a row vector. IJK. So IJK are the basis vectors. We haven't spoken about basis vectors yet, but exactly, you could describe you know, a vector in 3D space using these three basis vectors, I, J, and K. Another term would be the space is invariant under addition. Yes, exactly. Yeah, the invariant under addition, closed under addition. There's a multitude of terms you could use. Okay. So, in describing these qualitatively different kinds of vectors, first we talked about column vectors, now we're talking about row vectors. Oh, what is the topics, you say, Sly? Well, so the topic at the moment is I'm trying to give a non-rubbish explanation of what is a tensor. I mentioned earlier the sort of meme explanation of what a tensor is that a tensor is something that transforms as a tensor, which is a bit of a rubbish explanation. So in order to understand what a tensor is, we first have to understand a little more carefully what a vector is. Okay, so that's what we're talking about right now, vector spaces. So we spoke about column vectors as being, I denoted just as V, and I told you that these are elements of this vector space, this n-dimensional vector space. But there are other kinds of vectors, i.e. row vectors, and now this should be a different colour, which are elements of a slightly different vector space. And this slightly different vector space is often called the dual vector space. And I'll explain what a dual vector space means in a moment. So we will picture these elements of the dual space just as being n-dimensional row vectors. Okay, so this notation here means the dual to the n-dimensional, to a certain n-dimensional vector space over the real numbers. This star indicates that it's the dual. Okay, but you should note that dual isn't really anything special here. Okay, so Vn star, the vector space that is dual to Vn without the star, is still just as much a vector space as Vn without the star is. The dual thing is really just a matter of perspective. We could just as easily have said that our row vectors are elements of some vector space I call Vn without the star, and that would just mean that the column vectors that I've called V here would be elements of V star n. So this star thing is just, this idea of a dual is just a matter of perspective. You know, if you take the dual of something twice, it gives you back the original vector space you had before. But what does it actually mean, this dual space? So, oh yeah, so here is the statement that sort of convinces us that this idea of a dual space is not anything really different from the vector space we had initially, because the double dual of a vector space is just the original vector space you had before. Okay, now I've not proved that, and I'm not going to prove it, but you can take it as true. This is a kind of physicist's introduction to maths of tensors, not a mathematician's one. Okay, so formally we can talk about what a dual vector space is. And again, I mucked up the color coding for this. I tried to keep things blue about the dual vector space and orange about the vector space, but I seem to have accidentally switched it at some point. Two duals do not make a right. Well, in this case, they do. Two duals make a vector space, make the same vector space you started out with. So formally, the dual vector space is actually a collection of linear maps which will take you from elements of the original vector space back to the real numbers. Okay, so it's like we've got our vector space that I called V is a collection of all of the different n-dimensional real column vectors I can make. Okay, then the dual space is an instruction that is a linear map that tells you how to go from every single one of those n-dimensional column vectors back to some real number. Okay, it's a linear transformation that tells you how to go from those column vectors to the real numbers. That is what the dual vector space is, as I've defined it here. So we can understand how Vt, this transpose of V, or you know these row vectors now, are dual vectors to V, in the sense that if we define this linear map that the dual space represents as being multiplying these row vector elements of the dual space by the elements of the original vector space that are column vectors, then this just gives you, the magnitude of v, which gives you a real number. So in this sense, it does define a linear map from your vector space, which is your space here of n-dimensional column vectors, back to the real numbers. That is how these dual vectors, or row vectors, as we've explicitly called them here, define this linear map. Okay. So there are two ways of thinking about vectors. You can think about them as, so here now I've changed it the right way around. Here now vector space is orange, dual vector space is blue. Dot product, inner product, exactly, yeah. So I've done this at the moment without defining an inner product, because actually we don't really need to define what an inner product is to talk about these maps. An inner product would be, for example, how you would take two elements of the same vector space and combine them together to give a real number. Whereas this is actually about combining taking an element of the vector space and the dual space to give you a real number. So it looks qualitatively very similar because we've used this simple example of row and column vectors, but it's a little bit different actually. Okay, so there are two ways of thinking about vectors. We can think about them as elements of the vector space, which in our discussion we take to mean column vectors, or we can think about them as elements of the dual vector space, which we think of as row vectors. Okay. And now this is an important point here that, again, like I was saying earlier, there's nothing special about which one we've called the dual space and which one we've called the original vector space. We could just as easily have said the original vector space I called Vn. I realized that these funny n's I'm drawing here, these funny v's look a bit like n's, but they should be v's. I just wanted to try and distinguish them from v as an element of the vector space by trying to make it look a little calligraphic, but it didn't come out too well. But the point is, which one we call the original vector space, which one we call the dual space, is just a matter of choice. It's a matter of perspective. So here I've called column vectors the vector space Vn, and row vectors are element of that dual space Vn star, but I could have named it the other way around. Okay, so you can see that if you want to find linear maps that take you from the space of row vectors to the real numbers, then the space of transformations which takes you from row vectors to the real numbers is just the space of column vectors. And this map now that takes you from a row vector to a real number is just post-multiplying by this column vector here, which is the same multiplication we had defined before. Physicists really love to use letters to look similar to V, V, W, W, etc. Exactly. Is the arbitrariness of which is due to rise Z? What do you mean rise Z? I'm not sure what you mean by that. Non-dairy. It's just I think it's just a case of the fact that I suppose it's a consequence of the fact that the double dual is equal to the original space. So which one you call the original space is just a matter of choice. A dual vector space is still just as much a vector space as anything else you call a vector space. So somebody mentioned vector components earlier. So, the rise Z representation theorem. I actually haven't heard of that. Or maybe I've only heard of it by a different name. What is it? Establish a two-important connection between Hilbert space and its continuous dual space. Okay, this seems like a bit of a generalization to Hilbert spaces, which are slightly more complicated than, like finite dimensional vector spaces. At the moment, I'm just talking about finite dimensional vector spaces. So this subscript n I've given here will be a natural number. It will be a finite natural number. Whereas a Hilbert space, I think, in general can have, can be infinite dimensional. So it's quite possibly a consequence of that. Maybe I haven't thought about it formally enough. So now we can expand vectors as an element of the vector space. Mickey space is all I can handle. Mickey Mouse space. We can expand these vectors, these column vectors and these row vectors, in a component basis form, just as we're used to doing for any kind of column or row vector we've dealt with, in all sorts of mechanics and electromagnetism problems. Okay. So, for example, elements of this vector space that I've used to denote the column vectors can be expanded in this basis here, where we've got n column vectors, each one having a 1 in a different position, just a single 1 in a different position. So here this has got a 1 in the first row, 1 in the second row, and the same all the way along different rows until a 1 in the nth row. And by taking linear combinations of this basis set of vectors, we can describe any vector in this vector space representing all of the column vectors. BRB sandwich time. Enjoy your sandwich. Okay, so we'll denote these column basis vectors by EI. And it's actually important that this I here is a lower subscript, not an upper subscript. But until we get on a little bit more to talk about tensors in special relativity, I won't really say what I mean by upper and lower here. Here it's just kind of a notational thing, really. Okay, so we have a basis, EI, with a lower I that represents these vectors here. And then we represent the components of a given vector v by components vi, where now I use an upper index for v. Okay, upper index for the components. So we can expand any vector v as this linear sum over components multiplied by basis vectors. Okay, and it's quite a useful thing to point out that often people will drop this summation sign and will just write the component times the basis vector. This is often called the Einstein summation convention, and it's arguably one of Einstein's greatest contributions to theoretical physics, because it saves theorists hours of time writing down these summation signs. I mean, obviously he made a lot more brilliant contributions than that, but this is the everyday one that I thank him for pretty often. So, likewise for the row vectors as well, that are elements of what I've called the dual space, we can expand these also as basis vectors, as a sum over basis vectors with components, where now these basis vectors that I denote with an upper I, an upper index, are given by these. So these are all row vectors with a 1 in a single column of these vectors. Okay. So this is how you can construct vectors. This is how we've defined the sort of two different ways of looking at vectors. We've got vectors that I've denoted as columns, and then we've got dual vectors that I've expressed as rows. Okay, but from these two structures, so from this space of column vectors and this space of row vectors, we can actually construct much more complicated objects by thinking about sort of stacking multiple copies of these spaces on top of each other. Okay, because at the moment this is only describing n-dimensional vectors, either n-dimensional column vectors or n-dimensional row vectors. But a lot of important quantities are not just described by vectors, they're described by more complicated structures that will come in a second to call tensors. Okay, so say for example we take 2 copies of the space of column vectors of our original vector space, and we build a new object made from a pair of vectors that are each from 1 copy of this space. Okay, so let's say we've got a vector that I've given a little superscript 1. You're here paying attention. Well, I'm very proud of you, Atom Fighter. Thank you very much. So we've got one vector from this first copy of the vector space, and here these superscripts 1 and 2 I've given here are nothing particularly important, and actually we don't even really need to write them, and a lot of the times people won't write them. But this is just to show that we're thinking about two separate copies of the same vector space. Okay, so it's just kind of for my own bookkeeping. So we have a vector v from the first copy of the vector space, and another vector v, v2 now, from the second copy of the vector space. And what I can imagine now is building a new structure, building a new object, by combining two of these elements together. Okay, now I don't have to be too explicit about how I combine these things together. The sort of explicit way of saying what you're doing is to use this symbol here, which is a tensor product, which just means I'm taking two copies of this vector space and building a new object that is kind of the product of the two. But really, it's sort of just defined for our purposes in this way, in that I've built a new object that is entirely within this blob, and this object is constructed in some way from elements from the first vector space, the first copy of the vector space, and elements from the second copy of the vector space. Okay? So really this sort of product here, without going into too much detail, is defined by this idea that we're stacking different copies of elements of this vector space together. Okay? And often this is just written like this, where we drop these superscripts that describe which copy we were looking at, the fact that these are two distinct copies of the same vector space. But it doesn't actually really matter, so we can just often write it as this tensor product of these two vector spaces. Okay. So it's worth noting that the dimension of this new object we've created, that is really just taking all of the elements of one vector space, defining this as kind of one element of your new tensor space, or one component of your new tensor space, and then your second vector space, and defining this as the second component of your new tensor space. The dimension of this space, if the dimension of both of the vector spaces is n, will be n squared. Okay, because you've got n basis vectors from the first vector space here, and n basis vectors from the second vector space here. Then some terminology that the rank of this tensor space, is this similar to the dot product? No, it's sort of the opposite actually. So it's the dot product, if you like, takes two vectors and turns them into a scalar, whereas this actually takes two vectors and turns them into a tensor. Okay, it'll probably make more sense when we sort of explicitly write down what this thing would look like. Okay, but at the moment we can just think of it as we've got two collections of these objects, two collections of elements from the first copy of the vector space, and another collection from elements the second copy of the vector space. And using these two copies, we kind of sandwich these things together and create a new element, which has n dimensions from the first copy. It's got n basis vectors, and then has another n basis vectors from the second copy. So this new structure is no longer a vector, it's something different called a tensor. But we can be more explicit about how you can understand what this looks like in a minute. Okay. So the rank of the tensor, so it's a tuple. I think that's a terminology you can use for it. Yeah. Like would you call this a two tuple or something? If it's these two components, I'm not entirely sure on the terminology. But the rank of this space is really just defined. Is Vn not a tensor? No, Vn is a vector space. This space here is the space of objects that are kind of taken by stacking one copy of the vector space and another copy of the vector space, which sort of gives you an object with, instead of n dimensions, n squared dimensions. Okay. And the rank of this space is just a name for how many different copies of the vector space, the original vector space you're using to construct it. Okay. Okay, let you explain what you believe you want to say. Okay, go ahead. So, for example, if you stack p copies of the original vector space, which in our simple sort of example we're thinking about as being column vectors, and q copies of the dual space, which we think of as row vectors, then this gives you a tensor space that has rank pq, written in this way. Yeah, that's right. Vn circ Vn forms, well, it forms a tensor space. So Vn is a vector space, and then this tensor product of them is a tensor space. Yeah. Oh yeah, exactly. Okay. And then tensors will be elements of that vector space. Okay. And you could define them in terms of a basis, and the basis you construct for them would follow exactly from whichever basis you've constructed for your vector spaces. They would now just be, a product of these different, a tensor product of the bases you have for your vector spaces would form a basis of your tensor space. Okay. So that is what this rank PQ tensor space would look like. It's a product of P copies of the vector space and Q copies of the dual space. This space, again, in our case, in our simplified case, are these row vectors here and column vectors here. Okay. And just as a note, the dimension of this entire space up here is given by n to the power of the total number of spaces you have. So here we've got p vector spaces, q dual spaces. Okay. So for the case we're thinking about, where Vn just corresponds to the space of real n-dimensional vectors, as we've sort of been thinking about from the beginning, is what we've restricted ourselves to, then this product of one copy of Vn and a second copy of Vn can be understood as an n by n matrix. Okay, where you have to be careful about what these components are, where the dual and the vector spaces are the column vector and the row vector. Yeah, the dual ones I've said are the rows, and the one I've just called the vector space, so Vn here, I've just described as column vectors, and then V star. So these are rows, these are columns, in the way I've described things. Okay, but again, it doesn't matter. We could have defined it the other way around. The point is, there's nothing special about which one we think of as the dual space, which one we think of as not the dual space. Okay. So we can understand this structure here as being a space of n by n matrices. Okay. And because Vn, as I've called it here, so just V, this vector space, because the dual of a dual gives you the original space itself, so V star star is just equal to V, we can just as well think of V as being the dual of V star in the same way we think of V star as being the dual of V. Dual is kind of, in this case, sort of a relative term, as in if one is the dual of the other, it's also it goes both ways. If A is the dual of B, B is the dual of A, in this way. So, remembering the definition of a dual vector space is the space of all linear maps that take you from the vector space to the real numbers. That is what the dual to a vector space is defined as. So, likewise, this vector space Vn defines all of the linear maps that take you from Vn star to the real numbers. Okay? That is an alternate way of thinking about this vector space here. So, if we have a product of these two vector spaces V, we can think of this also as being the space, where is it? As being the space which will map two copies of Vn star. So we'll map, Vn star cross Vn star, we'll map these to the real numbers. That's another way we can think about Vn cross Vn. Okay. So I've written something here which maybe I think I need to be a little more careful with, but I think it's okay actually. So if we think about an element of this tensor space, so this is an element of, repeat that last part. Oh, so what I was saying was this whole thing of having V and V star is a relative thing. So V star is the dual of V. Oh, it's gone. Well, let me just write it. So V star is the dual of V, and V is the dual of V star. And remember, this definition of the dual space is that the space that is dual to the vector space V, this vector space here, namely, is the space of all linear maps that take you from V back to the real numbers. Okay, so like for example, these were these row vectors which by matrix multiplication take the column vectors to the real numbers when we multiply these things together. Okay, but likewise you could think of V, which is again the column vectors, V star is the row vectors. You could think of V as being the space of linear transformations that take you from a row vector to the real numbers. Again, just by multiplying the two together is how you sort of define this map. So it's a relative thing. So just as V star is, very sketching it, V star is a map that takes V to the real numbers. V is a map that takes V star also to the real numbers. Okay. Oh, that's no problem. It's perfectly fine to not get it right away. It's confusing, definitely. Okay, so what I've done here is I've kind of written out what an element of this tensor space looks like, sort of sketching what it looks like anyway. It'll have, components to it that come from the first vector space and from the second vector space. Okay, and the way that these, hang on. So this is a component of this tensor space here, as I've drawn it. And what I've said is that components of this tensor space will be linear maps that take us from two copies of Vn star to the real numbers. Okay. So they're maps that go from two copies of Vn star to the real numbers. So here I've sort of sketched out how they act on this structure here that is made of two copies of Vn star. So what they should do, this structure made from a product of two column vectors should take this structure that is a product of two row vectors to the real numbers. And the way they do that is in this way. Okay, so you have the same kind of vectory multiplication we had for V star taking V to the real numbers, but now we just kind of have two lots of it. So, this one here will take this one here to the real numbers, and this one here will take this one here to the real numbers. Okay, but actually the details of this are not too important, so we don't need to worry too much about this. Okay. Another point is that, hello theoretical phys. Another point is that Vn star crossed with Vn, so as in a tensor product. So the order is important. In this case, it is, yeah. It's just to show that we're associating, something in this sort of position here will map another copy of the dual space to the real vectors, but it may be sort of maybe not clear here to call both of these 1 and both of these 2? Well, actually, no, these both should be 1. This space here, v1, should map this particular copy of the dual space to the real numbers. Is it analogous to the dot product? It is, again, it's kind of a generalization. So the dot product is, takes you from 2 elements of a vector space to a scalar, to a real number. Whereas you could define, if you liked, you could define a dot product on a tensor space that would take you from 2 elements of the tensor space to a real number. In general, in sort of tensory terminology, this is known as a contraction. So you can also not just define a dot product that takes you from 2 tensors to a real number, but you could think of a product that takes you from 2 tensors, or even a single tensor, and gives you a different object, which is a lower rank tensor. Of which the dot product is an example of that takes you from two vectors to a scalar. That is in a way like a tensor contraction. Okay, if that makes some sense. A lot of this stuff, like I said, I think this is probably there's probably quite a niche audience for this, in that I suppose the way I'm talking about it, maybe you'd have to know quite a little bit about tensors already as it is. That hopefully it's, maybe we should do a longer discussion about this. Might be fun, and talk about this. Is this tensor products right now? Yeah, this is tensor products. Well, it's kind of just come to the end of it now, actually. So I was just talking about how you construct tensor spaces from vector spaces, what these sort of look like. So this is kind of the linear algebra perspective of what a tensor is. But, obviously as physicists, the thing we're most interested in about tensors is their kind of application to relativity. Special relativity and general relativity, where these things really come into their own. So that's what I want to start talking about next. How does this sort of abstract combination of different vector spaces give us something that is so useful in relativity? In order to UTU to make sense, they have to be 1 by n and n by 1. Why is that? What is it you mean by the order in which you multiply is important? That is what you're thinking. Oh, right. So, sure. So, like, so like here, for example, where I was talking about the dual space as being this space of linear transformations that takes you from the original vector space back to the real numbers. In this case, the order does matter which one you put where. You're right. In terms of the dimensions of the vectors, because a column vector is an n by 1 vector, a row vector is a 1 by n vector. So I define this map that takes me from the vector space, from a column vector to the real numbers, as being this product of vt, where vt is a row vector and what I've called an element of the dual space, where they're multiplied specifically in this order. They have to be multiplied in this order. Should it be transpose conjugate? Well, it would be if we were not dealing with real vector spaces. So we're really looking at a very sort of simple subclass of this, where we're only thinking about vectors with real components that are described by a vector space over the real numbers. But of course, you're absolutely right. If you're looking at another important application of this, which is quantum mechanics, where actually your spaces are, in general, they are Hilbert spaces, which are where this n here is really infinite. Actually, you have an infinite number. You have an infinite dimensional vector space. Then this would be over the complex numbers, and then you're quite right. Then this map, as I've defined it, the dual space, where is it? Where's it gone? This map that the dual space here enacts on the original vector space to take it back to the real numbers would be, the transpose conjugate here. Though actually, I think it wouldn't even have to, in that case, it wouldn't take you to the real numbers. It could take you to the complex numbers in this case. Yeah, but I suppose, but for the case of the case of quantum mechanics, actually, you would want it to take you to the real numbers, because these things would... Well, actually, no, even for a complex vector space, I think you want it to take you to the real numbers, not to the complex numbers. I actually can't remember now. If it's a complex vector... Well, yeah, it is, but what I mean is just in the definition that defines the structure of a vector space, does a complex vector space want to be, is the dual space defined as the space of linear transformations that take you to the field it's describing, so the field that the space is over, sorry, so the complex numbers, or does it have to take you to the real numbers? I actually can't remember. I suppose there'd be an easy way to look it up, which is just to type in complex vector space dual, and then see if it says it wants you to map to the real numbers or the complex numbers. And it says... What does it say? It says to the field, so it could be to the complex numbers. You would think complex. Yeah, I think it seems you're right. I guess actually, yeah. No, I'm getting confused. I'm making a mistake confusing the map that the dual space contains, these linear transformations the dual space contains, with the inner product. So the inner product of two vectors in a complex vector space should still give you a real number. This Hermitian product anyway should give you, yes, exactly, the norm goes to the reals. That's where I was getting a bit confused. Exactly. You're right, but the dual space, the set of maps that take you, the vector dual space is the set of maps that would take you to the field over which the vector space is defined, which in that case for a complex vector space would be the field of complex numbers. So you're right, it would take you to the complex numbers in general. So that is kind of a very, very rough crash course in what a tensor is in terms of linear algebra, missing out a lot of details, of course. I should maybe at the end I'll give some good recommendations for notes and links and stuff that I've found interesting and found useful. Tensors is a wholly interesting topic. Yeah, I really like all this stuff too. So now let's try and relate this discussion of linear algebra about vector spaces and so on to special relativity. And then I haven't written anything beyond special relativity, but we can also talk about how this is related to general relativity. Oh no, you've not missed anything about contravariant and covariant yet. No, this is nothing about that yet. So what I did was I cheekily sort of preempted it by, when talking about a basis for elements of the vector space, where is that? So yeah, in doing a basis component expansion for elements of the vector space, I gave them these names, EI and VI, where VI is upper, but I haven't yet used the term covariant and contravariant, and I'm not going to yet. Because really these terms don't have they don't really have any meaning when you're thinking about real vector spaces with orthogonal components, as we are here. When we're defining basis vectors in this way, which are totally orthogonal, where you've got a 1 in each element, and then likewise here you've got basis vectors that are also totally orthogonal to each other, there's not actually any difference between covariant and contravariant components. You can have a distinction between covariant and contravariant even in ordinary 4D real vectors without relativity, in a 3D real vectors, I mean, without relativity or anything. Yeah, exactly. Even Euclidean space still has these different components, but that's only true if your coordinate system is not rectangular. So if your coordinate axes, your x, y, and z axes are all orthogonal to each other, then your covariant and your contravariant components look exactly the same. But that is not the case if you have, say your axes are at a different angle to each other or something. Then that wouldn't be the case. So of course, when we talk about relativity, and particularly general relativity where your spaces are curved, this really is quite important. So I haven't yet used those terms, but we will come back to those. So talking about special relativity. So on is rectangular and orthogonal the same thing? Um, I suppose in the way I'm using them, they are. By rectangular coordinates, I mean like you've got an x, y, and z, where your x is orthogonal to y, is also orthogonal to z, and your y is orthogonal to z. So all of your coordinates are orthogonal to each other. Maybe there's some distinction between the two. I'm not sure, but you know what I mean, as in your coordinate axes form like the corner of a rectangle in 3D, or in n-dimensional, they'd form the corner of an n-dimensional square or something, okay? So to special relativity, let's think about the physics side a little bit. So we have this principle of special relativity that really says that the laws of physics should be the same in all inertial reference frames. Orthonormal gluten-free. Yeah, exactly. Orthonormal gluten-free coordinate axes. So all of our laws of physics should not depend on the inertial reference frame that somebody is in. Your laws of physics, the form of the laws of physics anyway, something like F equals ma. F equals ma should be true in every coordinate frame that is inertial. Every coordinate system that is related by an observer moving at a constant velocity relative to any other observer in a different frame, okay? That's what we mean by an inertial reference frame, and that's what I mean by the laws of physics should be the same in each of those frames. So we know from special relativity. Now the way I'm doing this is kind of assuming things we already know to then state a more fundamental underlying structure that is beneath them. So it's perhaps not the neatest way of doing it, not the most reductionist way of doing it. So there are some things here I'm going to state which don't necessarily follow exactly from what else it is I'm saying. But there are justifications for them. Just I think perhaps if I had to state all of the justifications for everything, like try and show in detail why it is you expect, why it is, space-time has this symmetry group that I'll discuss in a minute, or this part of this symmetry group, SO1, 3, this Lorentz group that describe the symmetries of Minkowski space-time, then we'd go on a little bit. So I'm just going to kind of motivate some of this. Yeah, the Poincare group is the full symmetry group, the full space-time isometry group of Minkowski space-time. But for illustrative purposes, I'm only really going to talk about the Lorentz group, which is kind of a section of the Poincare group that doesn't include space-time translations through space-time. It really includes the Lorentz group just describes these Lorentz boosts, that switch you between inertial reference frames. Okay. If you justify everything on stream, you would have to give a midterm. Yeah, that's very true. Okay. So we know from special relativity, assuming we know a little bit of special relativity, that to switch between inertial reference frames, we have these things called Lorentz transformations. And the most frequent case in which we use these, when you start learning special relativity, the main things you think about are measuring distances and measuring times. You think about time dilation, you think about length contraction. So for measurements of times and lengths, Lorentz transformations are these special classes of transformations which preserve the size of this quantity here. This quantity S that looks very much like the Euclidean distance in 3D space, but now with this extension to 4D, what is called Minkowski space, it includes this time interval between events. Now the claim I'm making, and I'm not justifying this, but this is something you can there are lots of different ways of getting to the principle of relativity, the fact that light should travel at a constant speed. There are lots of different ways you can approach relativity, taking certain things as fundamental and deriving other things as consequences. And I don't actually know which way I like the most. I tend to quite like the way of saying we have this length interval here, and this thing should be invariant whenever I change inertial reference frame. And of course, this thing here really is a consequence of the fact that the speed of light is a constant to everyone. If you're thinking about motion of light, so if you're measuring, if you've got a beam of light traveling through space, and you're trying to measure this quantity s squared between, the event where the light is released from here to the light being here, this value s will always be 0 along the path of the light. Okay, so the fact that the speed of light is constant in a vacuum, it sort of leads to this idea that this quantity here should be invariant. It shouldn't change no matter who's observing it, no matter what reference frame they're in. Okay. So Lorentz transformations, we can really define in terms of thinking about times and lengths as a transformation that keeps this quantity here the same. So when I take a Lorentz transformation, it might change delta x, might change delta y, delta z, and delta t, but this combination of delta x, delta y, and delta z and delta t should stay the same. That's what I mean by invariant. Okay. And transformations that preserve this interval have the structure of a group. Okay, they have group structure. Now, the concept of a group is something we could spend an entire other couple of hours talking about. But the extent to which I want to describe a group is that a group is an abstract structure that abstractly describes a symmetry in some way. So, there's this nice quote that numbers measure size and groups measure symmetry. So groups are structures that describe symmetries mathematically. Okay. But importantly, it describes symmetries abstractly. So it tells us that Minkowski spacetime should have this sort of symmetric structure of SO1, 3, but it doesn't really tell us anything useful as physicists in the sense that it doesn't tell us how physical quantities should transform when I go from one frame to another. So there is the slightly... what is the group operation? Well, the group operation will be compositions of Lorentz transformations. But again, this is slightly getting onto the next part, because really, the group here, technically this is a Lie group. It's a group that has, it's you can define an element of the group as a sort of continuous deformation away from the identity element. So there are an infinite number of elements, not an infinite number of dimensions, because you still have a finite number of, like a basis for this group. But there are an infinite number of elements because it's a continuous group. What does the comma represent? Well, the comma is just a name. So in general, a group like this, that sometimes you might write as SOP, Q, this special orthogonal group, it just means the group of the symmetry group of transformations which preserve lengths like this. So here, the 1 means we've got one part of the metric which has a minus sign in front of it, and then 3 parts of the metric which have a positive sign in this norm here, in this magnitude that is preserved for this invariant interval. For example, if you had like a SO2, 2, that would be like I'd have a minus in front of the x here instead. So I'd have 2 negative components, 1 positive. Could it be s, 3, 1? Yeah, again, this is a choice of sign convention. So sometimes you might write this as SO3, 1. It's all the same up to a choice of a metric signature, deciding to call time positive. And I think we had that debate last time with somebody that I prefer to have the time-like component as the negative in the metric, and then the space-like ones as positive, because then it is like it generalizes to Euclidean space if you had no time component, which I think I prefer. But it's all a matter of taste. And you're right, you could just swap them like that. Okay. So the point is that this symmetry here, so as I was just saying actually, so this is a continuous group, more formally what you call a Lie group, and elements of this group, or the group itself, is actually quite an abstract idea, okay? So the thing that tells you how to transform physical quantities is not the group itself. The thing that tells you how physical quantities transform are what we call representations of the group. And I'm not going to go into too much detail about what a representation is in representation theory because it's a big topic. But let me just talk about why the group itself is quite an abstract concept. So the sort of the modern, fairly abstract definition. Why would you want more negatives than you want to have? Exactly, I completely agree. The modern definition of a Lie group is that a Lie group is actually a manifold, a differentiable manifold, where operations in this group are defined as compositions of differentiable transition functions on this differentiable manifold. So it's a little bit of a tricky, definition to make, and it's quite a formal thing. But really, you can think of this group in the same way you think of any finite group, just as having a continuous sort of stream of elements to it, an infinite number of elements. Okay. But I don't want to talk too much about Lie groups because then that's, point is this all opens up an enormous kettle of fish, which is all very fascinating to talk about, which makes me think maybe I should have spent a little more time and just planned out maybe 5 or 6 different hours of stuff where we talk about all these things in depth. I guess we can still do that, but maybe yeah. And then the Lie algebras, of course, that is a totally different side of it. Another way of thinking about the Lie group is at the level of the Lie algebra. So it's an enormous topic, and it's all very interesting. Maybe I should plan out, a series of videos or a series of streams we could do talking about this stuff more carefully and more in detail. I guess this one you can think of as sort of the overview of what that might look like if I ever get around to planning that in detail, which hopefully I will. I mean, it sounds like a nice idea. I think it sounds like it would be fun for me anyway, because my understanding of this stuff, it would always benefit from a brush up, and I think when you have to try and explain things, it definitely makes your understanding better. So that's the point anyway, that the group is this sort of abstract description of the symmetry, which doesn't tell us actually how transformations that respect the symmetry are realized on physical quantities, how these things should change. So like we have this structure of the group, but we don't yet have explicit things like the Lorentz transformation matrix, for example. This would be an explicit way of taking a physical quantity in one frame and turning it into a physical quantity in a second frame and another inertial reference frame related to that one by some Lorentz boost. Okay. So here's what I've got. I've got the group is a description of the symmetry. And then I go on to say that physical quantities are built out of vector spaces, okay? Or they are scalars. So, things like velocity is a vector space. Then you can have, a casual discussion of GR that hasn't devolved into intricacies of the underlying mathematics. That's very true. Unless you're going to just talk about putting a bowling ball on a trampoline or something, or on a sheet of rubber, I guess you can't really talk about GR in a very sensible way without getting into a bit of maths. And we've not even got onto GR yet. This is still just SR. GR even generalizes this. Could be tensor spaces as well. Exactly, yeah, that's what I mean. That's what I was about to get at. So for example, you can, velocity as a physical quantity is something that is a vector space. Then you could describe the stress energy content of a system, this T mu nu that we've sort of written down a few times before, is a physical quantity that is described by a rank 2 tensor. So vectors and tensors describe the system, And also scalars do, okay? But we have to be careful what we mean by vectors, what we mean by, well, sorry, by what we mean by vector spaces, scalars, and tensors here. Because this is not just any old 4D vector in Minkowski space, okay? So when we were talking about vector spaces, I gave the impression that you could just kind of take, if you take any 4D real vector, that is an element of a vector space. That's certainly true. You can define a vector space as being the space of all 4D column vectors. That's a perfectly good vector space. But in special relativity, we have to be a little more careful, because now the principle of relativity tells us that all of our physical quantities, all of our laws of physics, which in the end, laws of physics are written down in terms of physical quantities, things like acceleration, force, mass for F equals ma, all of these things should transform in a particular way, in that when I go from one inertial reference frame to another inertial reference frame, the form of these equations doesn't change. Okay, so F equals ma should be true in any reference frame I like that is related to my initial reference frame by a constant speed boost. You always like to say vectors are tensors and tensors are vectors. That's true. Yeah, vectors are like a rank 1 tensor, and tensors are elements of, well, a number of stacked vector spaces. So how is the symmetry described by the group realized on a vector space? That is the thing we're interested in. So we know that space-time, Minkowski space should have this symmetry to it that describes Lorentz transformations. This symmetry group SO1, 3, as I called it above. But how are transformations that respect this symmetry realized in terms of transforming physical quantities? So that is where this question comes from. How is a symmetry described by a group realized on a vector space? So how do we express transformations which will change elements of the vector space, or transform a vector space to a different vector space? Rather, hang on. Transformations which will take elements of a vector space to different elements of the same vector space. How do we describe these transformations? Because at the moment we just have this abstract concept of the group. And the answer is through representations of the group. And this is another enormous and enormously important area that I don't want to get into too much. But the idea is that a group representation is a linear map from each group element that takes you to an invertible matrix. So vector spaces, transformations in vector spaces can be represented by matrices. So for an ordinary vector space that is, an n-dimensional column vector or an n-dimensional row vector, transformations on this space are represented by n by n matrices. That is how you describe linear transformations of the elements in this space. Exactly, and it's invertible because the point is that this group representation should preserve the structure of the group. So the idea of the group structure is sort of an abstract concept which tells you how group elements should combine to give different group elements, and it's restricted by a lot of these same properties that the vector space had, this idea of closure, in that if I take two elements of the group and I combine them together by this group operation, I should get another element of the group that is, another element that is still within the group, this idea of closure. And it's also an axiom of something being a group, which again, I haven't stated any axioms. Again, you can see this is a very slapdash kind of pretty mathematically quick and cheap introduction. All elements of the group should have an inverse to them. And if you're to preserve the structure of the group at the level of the representation, then that also means that your representation matrices that represent these group elements should be invertible, because that means they have an inverse, something that takes you to the identity matrix. So the identity group element should always be related to the identity matrix, okay, in this representation as we're discussing it. So, for example, for if you've got a physical quantity represented by a 4D vector, so here I've called this v, the v4 here, e.g. 4 velocity, this should transform as a particular representation of the group SO1, 3, the Lorentz group, okay? And what this looks like, what this representation, remember, is a linear map that takes you from each group element, each of these abstract group elements of, in this case, the Lorentz group SO1, 3, to some invertible matrix, which I've denoted by this double bar underlined RV here. This is a 4x4 matrix in this case. And this matrix here is an element of what is called the general linear group of V4. So the general linear group is the space of linear transformations, of invertible linear transformations of this vector space V4. So in other words, this is the space of all of all invertible 4x4 matrices. Okay? But you can see how we could write something more general, even if we weren't talking about column and row vectors here. We could be far more general. So that is sort of what our representation is. Our representation is the map that takes us from one of some of these abstract elements of the group that I've called just G here to denote one of these, to this 4x4 matrix in this case, which will transform elements of V4, these elements V of V4. So here are these 4x4 matrices. That should be 4x4 there. Okay, 4x4 invertible matrices. And for well, actually, I haven't. I should have written it down really. The way that these will transform, elements V into other elements V prime, is in this way. Okay. These transformation matrices here are these representation matrices of this sort of abstract symmetry group here. Okay. Again, this is all quite hand-wavy. I should maybe spend some more time on it, but I don't want to go too long, I guess. But if you imagine you've got a physical quantity that is represented by some tensor space. So this is a product of two 4D vectors, of these two 4-vector spaces. These, these 4D column vectors. We take a product of them, and we have this tensor space defined in this way. For example, the stress tensor, which describes, matter and energy distributions in relativity. It's a rank 2 tensor. So it is an element of this space here. So here I've written down again schematically what that looks like. You've got one copy, an element from one copy of the vector space V4 and an element from the second copy of the vector space V4. And this sort of structure here, that I've not explicitly written what it would look like, is an element of this tensor space. Okay. But matrices, but elements of this tensor space should also transform as a representation of the symmetry group, of a representation of SO1, 3. Okay, and the way that this representation looks like, what this linear map looks like, that takes you from the group elements to here, the general linear group of V4 producted with V4. So this is, the general linear group over the tensor space. So the group of invertible linear transformations that take you from one element of this tensor space to another element of this tensor space, I define in this way. So this is, how a tensor would transform under, in sort of matrix notation under like Lorentz transformations. Okay, so it's got two lots of this first representation from up here, GL V4, that kind of multiply whatever the thing you're transforming is in this way. Okay, this is kind of stating things rather than showing things here. But I suppose maybe it's helpful to kind of translate some of this stuff. What is that? So that just means this is a placeholder for whatever the thing is, whatever the element of this tensor space you're trying to transform, you would put in here. You would put your tensor, which for all intents and purposes in this description would look like a 4x4 matrix. You put it in here, and it'll transform in this way, by this product here of these matrices. Yeah, don't think of it in that way. Okay. So to kind of put this into standard SR notation, these elements of the vector space here are what we would call the contravariant components of the vector, and these elements of the dual space are what you would call the covariant. This one contravariant, this one are covariant components of the vector. And then the representation of these spaces, the representation matrices expressing these sort of explicitly as elements of this general linear group over this 4D vector space here. What was that? Oh, thank you, Destrez, for following. Very nice of you. We write these explicitly, these representation matrices, just as the normal Lorentz transformation matrices we're quite used to. And these are elements of, the group of linear transformations that take you from one 4D column vector to another 4D column vector, whereas these ones down here with the indices kind of switched over from upper to lower are elements that take you from one element of the dual vector space to another element of the dual vector space. Okay, so this idea of contravariant and covariant components is all to do with this vector space and dual vector space picture of these structures. And because you have these things importantly, these vectors and these tensors are now vectors and tensors that transform under this particular symmetry group we've defined, this SO1, 3 symmetry group. It's a consequence of that the way in which the covariant components transform is the inverse of the way that these covariant components transform. Okay, so if you were to multiply these two matrices here, they would give you the identity. Okay, these two Lorentz transformation matrices multiplied together would give you the identity. This last step, maybe this needs quite a little bit more talking about, because this is sort of the crux of it, I guess, relating this discussion about tensor spaces and vector spaces to how we're kind of used to applying them in special relativity. Is it necessary to indicate -1 for the inverse? You mean like put a -1 here or something? I mean, you could do, but I think generally, I suppose, people don't do it because actually the form that these things take is really just the same. Sometimes maybe, well, no, you wouldn't need to put a -1 here. I think it's swapping the upper and lower is fine just on its own, because this thing is an orthogonal matrix anyway, and it's symmetric. So actually, the way it acts on row vectors, its inverse is the same way it acts on column vectors. Because it's symmetric, these look the same anyway. If that makes some sense. Yeah. Okay. So if you build physics equations out of these representations of SO1, 3, then your equations will all transform between reference frames. When doing Lorentz transformations of your equations, they will all change in such a way that they are form invariant, that the form of the equations looks totally the same. Okay, so for example, say we describe the stress energy tensor of some perfect fluid in one reference frame. Then if we want to change to a different reference frame, we do a Lorentz transformation from this original frame S1 to a different frame S2, and what that has the effect of doing is just changing each of these components in such a way that the form of the equation is the same. These are still 4 velocities here, but now they're just 4 velocities in a different frame, and these p's as well change in a similar way, although they will get sort of mixed up and changed around what is a p and what is a rho. That will change, but the forms of these things here, which are 4 vectors, and this is a tensor, will not change when you change frame. Their components might get mixed up, but they will still be, this will still have components of, it will have a space-like component, C, well, it'll just have C, and then it will have, a time-like component, C, and then space-like components, U, where these things will just change by, by like a tittle or something, and it'll have a gamma out the front too. But the form stays the same, which is very powerful because now an equation you write down, a physical equation you write in one frame, when you take a transformation of it, a Lorentz transformation of it, the form of the equation will stay the same in the other frame, which is exactly really what we wanted from this principle of relativity, that the laws of physics, i.e. being equations of physics, should stay the same when you change to an inertial reference frame. Okay. So that is sort of how it works for special relativity. And then, of course, we could... Maybe I'll save talking about general relativity for another time, but I suppose the idea with general relativity is that now you have kind of a copy of this symmetry group defined at every sort of point in space-time, every local point in space-time. But then the issue is, well, how do I compare things like vectors and tensors at different points in space-time where these are, different copies of the symmetry group or something? So in that sense, general relativity is kind of like a gauged theory of special relativity, where it's just special relativity gauged at every point in space-time, rather than being a global SO1, 3 group. You have a copy of SO1, 3, or more specifically, a copy of the Poincare group at every point in space-time. So in that sense, general relativity is sort of like a gauge theory, really. And then, this also you can think about, so we've done this here, thinking about the group SO1, 3, the Lorentz group for space-time Lorentz boosts in flat Minkowski space-time. But you can think about different groups that, instead of describing space-time isometries, describe internal symmetries between fundamental particles. A gauge theory is one. So yeah, you typically represent internal symmetries of the standard model by gauge groups. But a gauge group is just a group that sort of has a space-time dependence on it. So there are like global symmetry groups where your fields transform. BRB, no problem. Where your fields transform at every space-time point identically the same, and sort of simultaneously exactly the same. But then there is the idea of gauging your groups, where now, instead of them all transforming simultaneously and the same at every space-time point, the transformation itself actually depends on the space-time point, which is a much more natural thing, really, if you think about what special relativity teaches us, that there's no such thing as simultaneity, or there's no such thing as absolute simultaneity. And you have this finite communication time between distant points in space. You can't instantly transfer information. Well, if you try to instantly apply a global symmetry transformation to all of your fields, or to think about what that would mean, it should make you a little uncomfortable, given what you know about special relativity, that you should be able to apply this thing or think about what its effect would be over all of space-time in the same way in one go, which is why gauge theories arise quite naturally, as as kind of inspired by special relativity, wanting things to be to respect special relativity and to respect this inability to communicate information instantaneously between distant points of space-time. There are beyond space-time symmetry groups or space-time isometries, like the Poincare group for flat Minkowski space-time. That's the space-time isometry group for Minkowski space. There are internal symmetry groups, which describe symmetries between fundamental particles, or more technically, they describe how fields that represent those fundamental particles transform amongst themselves. So, for example, in the standard model, we have quarks, and the quarks as a family of particles are represented by the group SU3. SU3 is the symmetry group that describes how quarks sort of transform into one another, and how these fields should be able to transform. They should be able to transform under the group SU3, and any transformation of SU3 shouldn't change anything physical, anything observable about these quarks. It's an internal symmetry of them. So this is kind of the way that sort of grand unified theories, well, not so much now, this is the way people, what sort of fields are we talking about? Well, so for quarks, these will be spinor fields, like a four-component Dirac spinor field. So it is a field as in like a quantum field theory, whereby instead of thinking about particles as particles, we think about fundamental object as being a field. And particles are excitations of this field, quantized excitations of the fundamental field. And there are, fields that represent the different kinds of quarks, and these things should be able to, sort of switch amongst themselves according to an SU3 transformation. So quarks themselves are, a representation of the symmetry group SU3. But this is all getting into a totally different area, which is very interesting. Again, why are things called gauge in gauge bosons? Well, that's because the symmetry group is a gauged one, in that the transformations which act on these fields are gauge transformations, in that the transformations themselves will depend on what point in space-time they are acting on the field. They're not global, as in the fields do not transform all the same at every point in space-time. They transform dependent on what their space-time position is. And the simplest example is a U1 gauge theory, that is for the unitary group U1. This is what describes electromagnetism. So if you decide that your theory of fermions should have a U1 symmetry to it, that is, that when I transform my fields amongst themselves by a U1 transformation, my physics shouldn't change. The things should stay the same. They have an internal symmetry that allows for them to be rotated amongst themselves by a U1 transformation. If you have this as a global transformation, where every single point in space-time, the field value, rather, at every single point in space-time is rotated by the same amount, regardless of how far apart these things are, then that is what you'd call a global U1 symmetry. But that is not very sensible, in the sense that if you impose a U1 symmetry, or rather, if you construct a theory, let's say, that has a U1 global symmetry, well, what that corresponds to is a theory that has one type of particle and a corresponding type of antiparticle with the opposite charge. But of course, like the case of thinking about what is the vector space, what is the dual vector space, what is the particle and what is the antiparticle, is ultimately a choice. It's a choice of labeling. I could just as easily call my particles having charge plus q and my antiparticles having charge minus q, as I could say my particles have charge minus q and my antiparticles have charge plus q. It's totally a matter of choice. And doing this global transformation, this gauge transformation, this U1 gauge transformation, really corresponds to making a choice of label, making a choice about whether you label this particular particle a particle, and then the corresponding opposite ones are antiparticles, which have the opposite charge. Which one you call with charge q, which one you call with charge minus q. Because ultimately it's a choice. But if you think about special relativity, think about these fields being, very, they fill the entire universe. These fundamental fields that describe are the underlying thing that describe fundamental particles. The more fundamental thing are the fields. Then why are you free to make a choice about what is the plus q charge, what is the particle, and what is the antiparticle at totally different ends of the universe? Because if you have regions of space that are so far apart that the knowledge that you've decided to call one particle plus q and the other particle minus q for the antiparticle might never be, or will take so long to reach the other side of the universe where you've made that same choice, it's sort of nonsensical to think that you can make that choice at both sides of the universe at the same time. Okay, a much more conservative thing to say is that within my, in accordance with special relativity, in some way that you haven't necessarily figured out, you want to make a choice that is consistent with special relativity, in that once you've made it at one point, the knowledge that you've made this choice will, travel off at the speed of light. Are you not allowed to make the thing that join instantly? Well, it's not that you're not allowed to, it's just that it seems a little iffy to make that choice. And it turns out that this feeling of iffiness is quite well placed, because to get rid of the iffiness, what you do is you decide instead to make the choice in a gauged way, where you define the charges or you define which is a particle, which is an antiparticle, in a way that is consistent with special relativity, in that there should be like a finite time it takes to communicate your choice from one set of particles to another set of particles. Yeah, it's sort of like that. The choices have to propagate at the speed of light, or rather, more importantly, they can't propagate faster than the speed of light. So the way you get around that is you decide that your symmetry group, your U1 symmetry group, should now be a gauged group, in that it's the transformation and therefore the choice of what is the charged particle, what is the anti-charged particle, will depend on your space-time position. So this just corresponds to turning what was a constant in your equations into, in general, a function of space-time position. And, you follow all this through, you do all the mathematics with this, and what you end up with So what I should say first is what you started off with is a theory of two particles, one particle, one antiparticle, which have opposite charges. And what you end up with is those same two particles, charged particles, one particle, one antiparticle, and a massless, uncharged boson, which interacts with both particles, i.e. the photon, something that translates, information about charged particles between one another. It can tell charged particles when to scatter off each other, when to repel, etc., thinking about it in that way. So this is all encouraging the fact that you want, what is a gauged group? Isn't U1 global transformation already a gauged group that leaves the Lagrangian invariant? It is, but so the gauged group, the gauged transformation, where U1 looks something like this as a transformation, where these are your generators here, or your parameters that tell you how much you're rotating by, and Q are the charges of your particles. But what I mean is you now take this generator to have a space-time dependence. So this, of course, here includes all of these transformations. It includes the global one within it, but it's substantially more conservative in that it doesn't presume that you can make this labeling or make this choice simultaneously at every point in space-time. So when you do this, when you introduce this gauge group, this gauge U1 group, this local U1 gauge group, rather than the global U1 gauge group, it gives you the photon. It gives you this massless gauge boson. I mean, this is why it's called a gauge boson, because it arises from a gauge group, which you didn't have before. You didn't have this from the global U1 group. You only get it from the local U1 group. So this is, of course, enormously encouraging. It tells you how you can start to think about constructing theories which contain these gauge bosons, these force-carrying interaction particles. And it's the same thing with QCD. So now instead of a U1 gauge group, you have an SU3 gauge group, and this gives you the gluon. And it also gives you all of the interactions the gluon can have with the quarks, and all the interactions the gluon can have with itself, and so on. So this is really the way that the standard model has been created, from thinking about these gauge theories and making these internal symmetry groups gauged, as sort of motivated by special relativity in this way, and it's been enormously successful. And I think what I was about to say earlier is that, more generally talking about groups and talking about tensors and stuff, this idea of finding internal symmetry groups, is really important, or especially, it's sort of in the later part of the last century, maybe just as much now. I don't know, actually, it's not my area so much, but in trying to construct these unified theories of physics, these grand unified theories. So people were very keen to try and find, a large symmetry group which contained within it all of the symmetry groups of the standard model. Like SU3, SU2, U1, all crossed together. All these groups of the standard model, to find a larger symmetry group which contained all of them, but would also have contained more things. So would have, described gravity perhaps, and the graviton, and what sort of internal symmetries that should have, and interactions with other particles, and etc. But it turns out that it's very difficult, actually, because, so what you have is you have space-time symmetries, like the Poincare group, or like SO1, 3 that we've looked at a little bit today. And then you have internal symmetries, like U1 and SU3 that I've mentioned. So what you might like to do is to try and think, well, how can I combine these two different kinds of groups and put them into one big group? And then I've got a single big group that describes all of all of my physics I'm interested in, all of my space-time symmetries, all of my internal symmetries. But it turns out there's a problem in doing that, in that you can't find a big group that kind of contains all of your space-time isometries and your internal symmetries. If space was a particle, what would it be called? Time is a chronoton. I don't know, what would it be called? Like a, I don't know. I was going to say like a positon for like position, but that would probably be quite easily confused with a positron, so maybe that's a bad idea. I don't know, that's an interesting question. A spaceaton? Yeah, that's not a bad one. I mean, would it be a boson or would it be a fermion? I mean, it'd probably be totally neither. I don't even know what that would mean to have a particle of a quantized particle of space-time. Well, yeah, so we talked about quite a bit today of totally really interesting stuff. Just I think it's hard to talk about it in extreme detail, but there's a lot of good ideas for stuff we could talk about in future. A lot more carefully and in-depthly, and I should definitely think about that. And if anyone has any suggestions, then please do absolutely let me know, and we'll think about those. But I guess for now, let's maybe look at a couple of memes for 10-15 minutes or so, and then I should really go and eat something because I've not had dinner yet. But yeah, also, oh, actually, that's another point. Also, there was a question also on the Google Doc that I've not got around to today, because obviously we were talking about this quite a bit. But so next week, or possibly over the weekend, if I can't think of something good to do for the spacewalk on Saturday, then I want to talk a little bit about tunneling and like quantum tunneling and other stuff like that, because actually tunneling is very relevant to my PhD work. But this is more about tunneling as in like phase transitions and stuff like that. Oh, no problem, Tyrion. So yeah, we're not quite done just yet. Now let's look at a couple of memes for a little bit. So hopefully my audio will not go crazy when I do this. Okay, is it fine? Okay, it's fine. Cool. Nice. So yeah, let's look at a couple of memes. I come back from experimentalists. You will never understand physics if you sit with a book and pen. You need to get up and start experiencing it. Theoretical physicists. Yeah, I'm not exactly sure how I can experience early universe cosmology, but thanks, Walter Lewin. This is getting out of hand. Now there are two of them. Electrons when they want to occupy more quantum states. I'll try spinning. That's a good trick. That's a good one. I like that Pauli exclusion principle joke. Europeans using SI units, Americans using imperial system, me who wants to use natural units, C equals H equals 1. I assume they mean H bar equals 1. That's the superior choice of H or H bar being 1 for sure. I like that though, that's good. That acting give me hives. Oh yeah, what is his name? Is it Jake Lloyd, I think? The actress that plays little Anakin, who then turned out to be like a... Harlem Snipes, the joke is getting very old. Okay. So true. Pimples? 0. Blackheads? 0. Air resistance in physics questions? 0. Quite right. Why would you ever consider air resistance? My kidnappers returning me home after I talk to them about rotational motion for 3 hours. Nice. Choros is the Greek word for space, and the space particle would probably be the choroton. Oh, that's a good one. Yeah, I like that. Very much in analogy with Choros and Kronos, I guess. I can't handle any more chaos. Upgrade. Triple pendulum. That's pretty apt. What we were doing over the weekend. Physics question. Assume the value of g equals 9.8 meters per second. My disappointment is immeasurable and my day is ruined. You gotta use 9.81. It just rolls off the tongue a lot better, I think. 9.81. What do I do while I have exams? Finding velocity, conservation of energy, kinematic formulas, power. Oh yeah, you would never use power to find something like that, I guess. Heard one too many lecturers containing the phrase symmetry protected during virtual APS. Introducing the Taurus symmetry protectors. This castle is symmetry protected. Is that like a Mobius strip on the flag? That's an interesting picture. Angular Momentum Edition is giving me a headache. Oh, I get it, because that's JZ, and it's like the Z component of Angular Momentum. Wow, that's like a contemporary popular reference I actually got. I'm proud of myself, to be honest. Hertz dipole. What is that? Is this an electron moving? The velocity of an electron? And then the dipole it produces by moving, I guess. That's, I suppose, a consequence of special relativity. That happens. You get these like magnetic field essentially produced by a moving charge. Who is Jay-Z? Jay-Z is Beyonce's husband, I believe. And also a musician. But let's be real, he's probably best known for being Beyonce's husband. I don't know any Jay-Z songs, but even I know some Beyonce songs, so if that's anything to go by. Electron behaves as a wave. Human being watches closer. Electron. Well, now I'm not doing it. Oh, the other... Oh, wait, no. Jay-Z's not Beyonce's husband, is he? Or is he? Yeah, no, I think Jay-Z is Beyonce's husband, yeah. Oh, I don't know. I think it is. Me telling someone will hang out after my... Lorodov? What is a Lorodov? I don't get that. Is this some experimental or computational meme I'm too stupid to understand? Oh, that's good. Different atomic models. Dalton, Thomson, Rutherford, Bohr, Schrödinger. Nice. Oh. Tungsten exists. Me, you dense. Blah, 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 blah. Tungsten is pretty dense. Very useful in old filament light bulbs. Opens computer. Andrew Dotson hasn't made a meme review for Pi Day. Oh, that is sad. Me after my quantum mechanics test. I don't know, actually, if I click that, I doubt you'll be able to hear it. Teacher. Ask doubt as many times as you want. Teacher asks doubt second time. Oh, student asks doubt second time. Teacher. Shut. I don't know what that means by ask doubt. Oh. Is it Iridov? Iridov is a physicist who wrote a book on physics that has many repetitive and draining problems. So the joke is that you will never finish them. Oh, I wasn't aware of that. Interesting. Okay, thank you. I am so heat right now, it's not even cool. Physicists. Ah, yes, enslaved entropy. Okay. People who celebrated Pi Day on March 14th. People waiting for July 27th to celebrate Pi Day. Me waiting for Euler Macaroni Day. Oh yeah, that's because 22 over 7 is a very close approximation. Well, not a very close approximation. You know, it's a decent approximation to pi, to the first few decimal places. How to measure the area of your cat. Aw, that's wholesome. The T in T bar stands for trans rights. Interesting. Oh, T bar is a wrestler. I didn't even know that. I'm not sure. What is T bar in a physics context? I don't know if that is a constant. Just T divided by 2 pi, I guess, by the standard convention of what bar means. Taylor's approximation is to physicists what pi equals 3 is to engineers. Literally every formula for everything other. Taylor expansion. Very true, very true. Oh, okay. That was weird. Okay. That dude is getting blocked. Just approximate, mate. Neglect friction. Frickty off. At least according to my teacher. Blah, blah, blah. My father said, what are you doing while I made this meme? High school physics exists. Air resistance exists IRL. Students wear air. Okay. Drip velocity. What on earth is that? Oh, drift velocity. I don't know what drip velocity is. Friction off. Yeah. Oh, I see. Yeah. I think my brain wasn't even focusing on that. Using the Drake format, using the great Drake formula. Ah, I see, like the Drake format meme. Nice. Professor, so today we will learn what happens on the event horizon of a black hole. Student, what? It doesn't happen. That's true. Well, I mean, from the perspective of someone watching anything fall in, it's true anyway. Today's not important. Me, 14th of March. Pi Day, Einstein's birthday, and when Stephen Hawking died. Oh, sad. Learning a shit ton of laws, physicists, lawyer. Pretty accurate. Neutron stars be like, I have a proton, I have an electron. Neutron. Okay. Yep. We definitely stan Euler-Lagrange over F equals ma. Germans when Americans pronounce Schwarzschild radius. I mean, yeah, I'm pretty sure I say that totally wrong as well. Well, I mean, maybe it's Schwarzschild, I don't know. Sly will know as a German, but I'm not totally sure. Oh, poor cat, poor cat. Making it do quantum mechanics. Nice. I will name my son Physics, then I'll become the father of physics. If only. Schwarzschild. Schwarzschild. Yeah, that's basically how I say it. Okay, one German word at a time. Sounds good. All these Pi Day memes. Classy. Wow. Are they gonna fall? Oh, I wanted them to fall. I guess it wasn't a good idea to take GR as an undergrad. Me curious about GR, tensors and manifolds, Einstein field equations, Schwarzschild geometry, Kerr geometry. You really do get down the rabbit hole. Wants to become a physicist? Me. Struggling with the easiest maths problems. That is definitely me. Absolutely. Air resistance exists. Physics questions. You have no place in this story. You come from nothing. You're nothing. You know what? F you. Unthevenins your circuit. I don't know what that means. I mean, I know what Thevenin is, as in Thevenin's theorem in electronics. Me after learning some basic chemistry after doing physics for too long. What am I supposed to do on this question? Just to explain, you don't need to calculate anything. Pretty much. Wait, is entropy increasing? Always has been. Very true. Controversial. Me after learning Lagrangian in classical mechanics. Me after encountering Lagrangian in CFT, GTR, and QFT. Is GTR as in GR? I've never seen anyone call it GTR. wonder if anyone has commented on that. What did they mean by... Oh, general theory of relativity. Ooh. Why would you call it GTR? That's weird. At least for the symmetry, call it like GRT, general relativity theory, but GTR, that's weird. Undergrad EM would have gone so much harder without Griffiths to hold my hand. Thank you for changing my life. I'm literally a textbook author. Griffiths' books are great. I love his elementary particles book too. That's brilliant. Yeah, they did mean GR, I think. Yeah, not GR, GTR. Well, I think I might leave it there now, chaps and chapesses. I think I need to go get some food now. So, yeah, thanks for coming to hear me ramble about tensors for a bit. And I'll see some of you on Thursday where we'll play some Mario Kart and chat a little bit more. And then maybe on Saturday, I'm not sure what to talk about. Ideally, it'd be like another spacey Saturday spacewalky thing, but I'm not totally sure about what to do. So if anyone has any suggestions, you know, as usual, feel free, if you're not already, to join my Discord. Yeah, suggest there what you think we could talk about on Saturday. Maybe we could just talk about tunneling on Saturday. Either one, I'm not sure. Let me know what you think. But yeah, Mario Kart on Thursday, and then I'll see some of you guys then. But hopefully talk to you before on the Discord anyway. But yeah, okay. See you guys soon. Bye. Bye. Oh, thank you for the. Oh, that is my. Sorry, that's an email that's just come up. Thank you for the bits, Theoretical Fizz. That's very nice of you. Yeah, so I'll see you guys later. Okay, bye. Bye.